Hi, everyone. So, welcome to Quantum Computing today. Today is a different setting. We will have a guest lecture first, and I'm very happy to have Rolf Heuer here. Rolf was the Director General of CERN, so the European Organization for Nuclear Research, where I worked in the past, and Rolf was the Director General at the time the Higgs boson was discovered. So a very important moment of time. Now, Rolf, you have been retired, I think, for almost 10 years or so, but you still keep working all day long, I feel. And Rolf and we work together on some special projects, also helping politicians to better understand AI. And we were earlier this year in Jordan and had a conference for members of parliament and senior staff of parliament administration and helped them to better understand AI. And I'm very happy to have you here today in my quantum computing lecture so we can hear a little bit from you about CERN and some application of quantum mechanics eventually. So thank you very much for joining today, Rolf.
Yeah, very welcome. Thank you for the invitation. And actually, there will be nothing about quantum mechanics or application because I would speak to the converted. So I try to give a different twist to this talk. I called it exploring. First of all, do you hear me well? I hope so. And secondly, you see my screen. Okay. So, exploring the early universe and with a slight touch of also science bridging cultures and nations, because that's very close to my heart. So, what is the scientific challenge of particle physics? Well, it is to a large extent to understand the very first moments of our universe after the Big Bang. So at the moment of the Big Bang, the universe was extremely hot, extremely energetic, and extremely small, and then expanded over time. And the time was nearly 14 billion years to the size of today, which is 10 to the 28 centimeters. So it expanded isotropically in all directions. And astrophysics or astroparticle physics uses telescopes to look into the history of the universe. So what they do is they look into the universe and see what happened millions or billions of years ago. Particle physics is different because astroparticle physics, when you do it with visible light, stops at 380,000 years after the Big Bang. It cannot go beyond that because at that time, in the early times of the universe, it was so hot that no light, no information could get out in the form of light particles. That means in the form of photons. So 380,000 years is a sort of wall against which astroparticle physics has to work against. Now, particle physics, we are using our accelerators as a sort of microscopes, not to look back into the universe, but to reproduce the conditions of the early universe. So we are not looking back, we are really reproducing, trying to reproduce what was happening at that time. If I look onto this on a ruler, you see at the end of the ruler on the bottom right, the universe of its present time, and then you see there are some Earth-based or space-based telescopes like ALMA, VLT, or AMS, the Alpha Magnetic Spectrometer, and Hubble. With our accelerators, we are getting closest to the Big Bang. Nobody else gets closer. We are getting as close as roughly 10 to the minus 12 seconds. So in other words, we are sort of breaking the wall of the hidden universe, hidden to the astrophysics, to the astroparticle physics. And what we know today is, of course, what you all know is matter consists of molecules, which consist of atoms consisting of nucleus and electrons. The nucleus consists of protons and neutrons, and the neutrons and the protons consist out of quarks, the up quark and the down quark. These are the smallest not divisible the smallest stable particles which cannot be divided in subcomponents, according to our present knowledge. And out of this, we have the standard model of particle physics, which describes this microcosm with which one can really reproduce the conditions of the Big Bang, shortly after the Big Bang. Our visible world consists out of 6 quarks and 6 leptons. And only 3 of these are needed in order to really construct the visible world. That's the up quark, the down quark, which make the protons and the neutrons, and the electron, which together with the quarks make the atoms. Now, the forces which act between quarks and leptons are the following 3. The electromagnetic one, which is transmitted by the photon, the strong interaction, which is transmitted by the so-called gluons, and the Z and W bosons, which are transmitting the weak force. The weak force, for example, is responsible for the condition for the reactions in the sun. The strong force keeps the nucleus together, and the electromagnetic force, for example, keeps the atoms together. Now that is all very nice. You know, there's a force which is gravitation, but it's so small that fortunately in particle physics we can neglect it. So these 3 forces, they are the ones which act between quarks and leptons and which we can use in order to rebuild these reactions. Now this all would work very nicely in a world with massless particles. Now, but if it would be massless particles, no composite matter could exist, because massless particles travel with the speed of light. There's no composite matter possible. So somehow all these particles must have received mass or must receive mass. And this is one of the biggest questions in particle physics until roughly 10 years ago. That was the last missing briquette in the bridge of the standard model in the so-called Higgs boson. Together with the Higgs boson, that is the standard model as we know today. But how did we get there? And this I want to show you to some extent how long it takes and what it takes for the discovery of this standard model. It's a sort of subjective stroll through roughly 50 years of particle physics. And I hope I can convince you it's a success story of collaboration and cooperation. It's a success story of scientific strategy and a story about precision, because precision matters in order to get forward. Now you might wonder, why do I need collaboration or cooperation in science? I thought we think science is competition. But there's no good science without collaboration or cooperation. You need competition and you need cooperation at the same time. So you can take it together into another word, co-opetition, so to speak. But both are really necessary to do good science. So roughly 50 years, 60 years back, in the late 60s, in the early 70s, the theory colleagues, they formulated the electroweak theory, the basis of the standard model. They applied current ideas to the gauge theory in order to formulate a theory bringing together electromagnetic and weak force. That was then also for Weinberg and Salam the Nobel Prize. Then a few years later, it could be extended to the hadrons, the quarks, assuming 2 quark generations. And they postulated a new quark, the charm quark. And then it was 3 years later, again enlarged, assuming 3 quark generations. The top and the B quark were postulated in 1973. And that explained how CP violation could happen, which was discovered in 1964. So that was then, at that time, the standard model, the experimental status of the standard model in the early 70s. You see, only 3 quarks were known experimentally, 4 leptons, the electron and its neutrino, together with its heavier brother, the muon, with its neutrino. And of the forces, one knew just the photon for the electromagnetic force. So at that time, one needed then new experiments, and they were constructed mainly in the US and in Europe. And I take as an example the one where I started to work, and that was 1978 at DESY. The first beams were stored in the Petra, the new electron-positron storage ring, delivering a maximum energy at Petra of 47 GeV in the center of mass system. 4 experiments had been installed: JADE, Mark J, Pluto, and Tasso. And JADE was the experiment I was working on, and the abbreviation stands for Japan, Deutschland, England. And I have here the best possible drawing of our detector. And unfortunately, a person is missing here, but was roughly the dimension of 4 times 4 times 4 cubic meters. That was the size of these experiments at that time. And what were we studying? Well, we had, you see it on the left-hand side, in the space-time diagram, we were studying the collisions of electrons and positrons on the left side. We had the exchange of a photon decaying into producing fermion and antifermion. So all matter particles, leptons and quarks, are fermions. So you produce fermions and antifermions. Now, if these fermions are electrons or muons, you find in your detector straight tracks which are going out of from the interaction point back to back. It's different for quarks. You see on the left-hand side electrons and positrons colliding and then producing quark, antiquark, but quarks are not freely accessible. They are never free. They are always bound through a exchange of gluons, which are here the curled tracks in the middle of the drawing in the QCD part. And then these quarks and gluons, which are produced from the original quark and from the original quark, they form then hadrons, which then decay, and these particles are visible and can be seen in our detectors. So you measure the event shapes in the detector. This is a cross-section through such a detector. You see, for example, in the second plot, quark and Q and quark and antiquark, or fermion, antifermion, going back to back with a few other tracks. So this is an easy signature of 2 quarks really going essentially out of the detector. On the right-hand side, you see more quarks and gluons. The black tracks, the curved ones are gluons, the straight ones are quarks. So you see, you go essentially from a pencil-like event to a spherical one. So you can construct, define variables like thrust in order to analyze the structure of these events where the hadrons were produced. So if you have a pencil-like event, the thrust is more or less is very close to 1, because the thrust is the momentum along the combination of momentum along the line of flight of the quarks. If it's a more spherical event, then the thrust is much less, because it is divided not only along, it's not only seen along the line of the quarks, but also along the line of the gluons. And the mixture then gives a maximum value or minimum value of 2/3 compared to 1 in the pencil-like event. So if you have electron-positron going to QQ bar with a gluon, you define jets. The jet is a highly collimated bunch of particles, can be energetic points in the calorimeters or can be tracks in the tracking chambers, which can be relatively easily be found after visual analysis of events. And then you have to think back to 50 years. We really looked at these events by eye. We not only used computer programs, because these were only developed at that time, slowly developed. We really scanned events for specific effects in the event pictures. But in order to compare then the observables based on the jet momenta, for example, with using thrust, with the theory, you need an objective and unambiguous jet definition, which can be used by experimentalists and theorists on equal footing, because otherwise you cannot compare experiment and theory. And that gives you one example of such a thrust distribution of different events for different energies of the collider. So on the top left, the collider had a center of mass energy of 14 GeV, then going to the right to 22, on the bottom left 34, and then bottom right to the maximum of 44 GeV. And you see the distributions look relatively similar, but nonetheless different enough to compare it to different theoretical models. And what is displayed here are the experimental points, which are the black dots, and two different models. One model where the quarks do not have, in addition, gluons in the events. These are the dashed ones. And the full lines is a model with gluons. And what it means, you see on the right-hand side, you see quarks originating from the middle of the event, quarks and the gluon, which are, so to speak, still connected through the gluons in the bottom part of the picture, where the gluons and quarks also decay and form a sort of, how to say, sea of, a sort of sea of quarks and gluons together, which glue the whole event together. And that is a so-called Lund model. And there was excellent agreement with the data on the left-hand side. And therefore, what you could conclude is that the quarks which appear which are produced in the collisions, they also have quarks with them. So it is really the strong interaction really is composed out of quarks and the gluons of the exchange particles. If you carefully select a typical event, you see on the left-hand side here, by eye, two quarks, a quark and anti-quark, back to back, with tracks in the middle part of the ring, and energy clusters in the darker outside ring in the calorimeter. And on the right-hand side, you see one high momentum gluon being connected to the two quarks. So this is a striking example of how you can see specific events at that time. And what you see here is the nicest event display available at that time. We were still in a rudimentary form looking at these events. And if you have two quarks and one gluon, they should form a plane. And the planar events are the signature for gluon radiation. And that was in the year 1979, the basis for the discovery of the gluon. It was on the basis of such events and of distributions which I just showed that we found at Petra at that time the gluon. But then you can, of course, study the jet production rates in the energy range of your collider, which started at 22 and went up to nearly 50 GeV. And we could publish in the collaboration the first experimental investigation of the energy dependence of the strong coupling strengths. the energy dependence of the coupling constant alpha S. Since it's a non-abelian theory, the strong interaction, the QCD, you expect that the coupling constant is not a constant, but that it runs with energy. And you see on the right-hand side, the status 1989 with the black dots, previous experiments at lower energy, and the two red dots, the new experiments at Petra for the strength of the strong coupling constant. And you see for the first time that it really is reduced in strength the higher you go in energy. So that's the first time the energy dependence of the strong coupling constant was proven, and the first time that people really started to believe in the quantum chromodynamics, in the description of the strong interaction between particles. But we expected, of course, more. Everybody was searching for the top quark, which was postulated, as I said before, early in the 70s. Now, theoretical prediction for its mass were rather variable. You could vary from 10 to 20 to 30, 40 GeV. And you could see here a result from the experiments at that time. There was no resonance for the top quark visible. There was nothing special. And the two dashed lines on the right-hand side indicate what you would expect without a top quark, that's the lower dashed line, or with a top quark, that's the upper dashed line. What is displayed here is the ratio between the production rate of hadrons, that means quarks, antiquarks, normalized to the production rate of a muon pair. And of course, if you have one quark more, you must have a higher production rate, and therefore the dashed line with the top is higher than the one without the top. But there was nothing really striking. So what we did then, we made an energy scan. So you scan through the energy of the accelerator step by step. And of course, at that time, we had already an online analysis program, which was this one. That means it was handwritten. At that time, we did not have yet anything via the computer, not thinking even of any quantum computer or AI. So that was the JADE online version of the R-plot. And you see, you can, with good eyes, you can see the dots of the data and the imagination of the shift crew, how a resonance would look like in these data. We also had, and that's a joke now, a new classification of results. If you have a look on the right top, and the new JADE classification was JADE incredibly preliminary, as you could well imagine. Okay, there was no top, so we went back to the strong interaction and then also to the study of electroweak interference. Now, when you unify electromagnetic and weak interaction, you have an interference between the different forces, between the different exchange particles, the photon, the Z and the W, and that gives you either a positive or negative interference. And in 1986, we could publish then the reaction electron-positron into a muon pair as a function of the different energy. On the top left, 14 GeV, on the bottom right, 44 GeV. And what is displayed is the reaction rate as a function of the angle along the beam axis, the collision axis. And you see two different estimations. The dashed line is just the electromagnetic, what you would expect from an electromagnetic exchange. And the full line is what you expect from electromagnetic plus weak interaction, including the interference. And you see at a small energy like 14 GeV, both lines are essentially indistinguishable. But if you go to higher energy, you see a very nice, slowly distinguishing very nicely the weak from the electroweak interaction. So that was one of the first proofs that electroweak unification seems to work, because you could observe the effects experimentally. And that's plotted here for the different center of mass energies, here in this case squared. You see the straight line from left to right is a QED only, the electromagnetic only, and the one which goes down is a standard model with an exchange particle of Z0 as an exchange particle of 93 GeV mass. And our data fit very well the standard model with a mass of the Z0 of 93 GeV. So already at an energy of maximum energy of 44 GeV of the accelerator, you could see effects far beyond the reachable energy, namely virtually 93 GeV. So the lesson number one is that precision measurements indicate the path to physics beyond the present energy reach, because you have the effects of higher order corrections in your theory, which are visible in the experiments. So that brought us in the mid-80s then to the experimental status of the standard model as displayed here. So the three particles were not yet, three hypothetical particles were not yet discovered. The top quark, the neutrino belonging to the tau, and if it exists, the Higgs boson. All the others had been discovered, the Z and the W at CERN, at this superproton synchrotron, just before the switch on of a new accelerator called LAB. So further progress in order to detect and investigate these particles needed progress in experimental techniques, namely the accelerator and the detector. Needed it in theory, both have to go hand in hand, and as you will see also later, in cooperation between people. Remember, the J detector was a purely German detector. No, sorry, wrong. The J detector was already a non-purely German detector. It was German, Japan, and UK. Now, with the larger detectors, with a larger accelerator, you needed many more institutes all over the world. And exploring the early universe further, you also need to go to a larger laboratory. So you not only need larger and better experiments, you also need larger infrastructures, international collaboration, as I said, and as a basis of all that, you need trust between the partners. And this is a nice thing. If you have an international collaboration, you learn a lot about your partners and trust, and about the trust between partners. In one word, it needs an institute like CERN. And CERN is a well-established particle physics institute. And it has essentially four pillars. Of course, research on the top. But research cannot be done without the basis, which is at the bottom here, technology and innovation. It cannot be done on the right-hand side without collaboration. And it needs people. It needs good people. That means CERN is educating and training and doing outreach. And with all four pillars together, we could move forwards in our theoretical and experimental and cooperative adventure. And the first one was then to construct the electron-positron collider lab at CERN. And you see it here embedded in the landscape, so to speak. It's near Geneva, and you see the large blue circle is 27 kilometers circumference of the lab ring. It's in a tunnel on the average 100 meter underground, because we had to select, or one had to select the right stable formation of the ground. So one had to go pretty far below the surface. And it's a bit skew. At some places, it's only 40 meters. At other places, it's 140 meters underground. LAB, in contrast to Petra, had a maximum energy factor 5 higher, 209 GeV. Started delivery of data in 1989 until the year 2000. And again, 4 experiments, Aleph, Delphi, L3, and Opal. And that's the best figure I could find here for the Opal detector, which was a successor, so to speak, of the Jade detector. It was the same groups of Jade, but many more other groups joining. And again, there is no person here, but to give you an idea about the size of the detector, the red part inside is the so-called tracking chamber, a drift chamber, which its size is roughly the same size as the whole Jade detector was at Petra. So you see also the detector is much, much bigger, finer granularity, and many more possibilities. We had roughly 300 to 400 members, 300 to 400 scientists working in this experiment, compared to a few 10 in the Jade detector, at the Jade experiment. So already a factor of 5 to 10 more people involved in this experiment. And the main research topics at LAB were to measure the properties of the W and Z, which were discovered at this super proton synchrotron at CERN already a few years earlier. And we had this indirect evidence at Petra already, which was very exciting at that time, and which I showed a few minutes ago. But we wanted to search for the top quark, search for the Higgs boson, wanted to do precision measurements in the strong interaction, and wanted to do many precision measurements in order to guide our research beyond the lab energies, beyond the, at that time, reachable energies. And these were expectations a few years before the switch on of lab. And you see the statement here, the overall conclusion, it's written on the top. The overall conclusion is that at lab, that Z0 mass and width can be measured with relative ease down to 50 MeV, plus minus 50 MeV. And the vertical scale is determined by the normalization, which is done by the luminosity. That means a special reaction in the collider, with roughly a precision of 2%. And therefore, one was guessing, first of all, the 50 MeV, and was guessed that the width of the resonance could be measured with roughly 10 MeV uncertainty. And it was stated very carefully, might be possible. Okay, so these were the expectations. The first thing was that we could have a very strong highlight, namely the measurement of the Z0 mass gave a clear statement that there are only 3 light neutrinos, and therefore 3 generations of quarks and 3 generations of leptons. And you see on the right-hand side the combination of the data after the 10 years of running of the 4 experiments, an average measurement error bar is a factor of 10 smaller than you see on the plot. And you can clearly distinguish 2 neutrinos, 3 neutrinos, and 4 neutrinos. So the green line is the 3 neutrinos, the 3 light neutrinos. But how accurate could we measure at the end? And you see the width could be measured much, much better than the estimated 50 MeV. And the number of neutrinos was determined to a very precise number of 2.984 with a very small error bar of 0.008. Intriguingly, if you don't find anything, by the way, which is more than 5 sigma, and therefore a discovery, you look at each sigma deviation, and there was intriguingly a 2 sigma lower number in all experiments for the number of neutrinos. So a little 2 sigma below 3. But why could we measure so precisely? Well, okay, that I had already said. because the normalization made fantastic progress, not only in the measurements, that means in our experiments, but also by the theories. There was enormous theoretical work being done, which reduced the error bar in theory by by big factors. And also the experiments installed new detector pieces with much lower tolerances, excellent understanding of acceptance, and therefore we achieved much more accurate measurements. And as a matter of fact, that allowed us these very highly precise measurements of the mass of that Z0 and the width of that Z0. And actually, a nice effect was that 10 years later, after the lab era, new calculations, new findings of the old data resulted in a correction of the 2 sigma tension. It went away. The 2.98 went up to 2.996. So fantastic success, not only of experiment, but also of the theory and of the standard model. So the lesson 2, precision physics needs progress in theory and in experiment. Both have to go hand in hand. Now you remember, hopefully, the electroweak results at Petra. These two plots I had shown, and from Beate Nauerska's 1986 physics report. And if you now take in not only these measurements, but also measurements at lab, then you see this. You see this precise measurement of the electroweak interference, the asymmetry in the reaction electrons to muons. You see this fantastic part up to 40 GeV or 44 GeV from Petra, then at 50, 58 or whatever GeV from an experiment in Japan, and then going through the resonance at lab, through the Z0 resonance at lab. Again, a fantastic confirmation of the calculations done in the electroweak theory. But the strong interaction also delivered quite very nice results. The running of alpha S, I showed you already at Petra, but now, including the lab data, look only on the right-hand plot. And you see on the bottom right, on the right-hand plot, you see the results of the 4 experiments at lab. And combined with the experiments at lower energy at 20 or 30 and 40 GeV at Petra, you see very nicely the running of alpha S. Again, higher precision, better results. And look at the most accurate measurement at lab. If you have good eyes, you see the purple dot, that's from alpha, the purple triangle, which is from opal. It's the best measurement, it's the smallest error bar. And this, I find a striking plot here. This is the progress within 10 years with the results from lab and other experiments. It's a world summary of measurements for the strong coupling constant. Status in 1989 on the left, status in 2000 on the right. And what a striking result of the running of alpha S with all these data. It's fantastic. Sometimes I can get excited about these results. But one can easily also now go beyond 3 jets. I showed you these nice 3 jet event. Now you can now estimate with a lot of data at lab the production rate of 2 jets, 3 jets, 4 jets, and that's displayed here in red what you expect from the theory, and in green what you have measured at the experiment. And you see you can distinguish on a statistical basis 2 jets from 3 jet events, 4 jet events, 5 jet events, and more. And therefore, you can test quantum chromodynamics at a much, much better level with all these different analyses and parameters. Also, the properties of jets can be nicely evaluated. Like you expect that gluon jets, because they disintegrate into quarks, gluons, etc. So you expect them to be wider than pure quark jets, and this is plotted here on the bottom in the bottom plot. You see on the left hand, the left peak is what you expect for jets without gluons, and what you expect in the wider peak, what you expect from gluon jets. So quark jets are much narrower than the gluon jets. And how did you identify the gluon jets? Well, if you produce two Bs, a bottom and an anti-bottom, then they can only afterwards decay into a gluon. They can only have a gluon at the end. They can only now how to explain. You can easily identify the gluon once you have identified the jets on the quark jets, and you do it because the bottom quark is long living, so it has a secondary vertex. It decays inside the detector, and you find secondary vertices. By this, you identify, you tag the bottom quarks, and then you know the one which is not tagged is a gluon jet, and therefore you can measure then easily the gluon jet. I'm sorry, that took me a little bit. I'm a little bit unconcentrated because of other problems. And then LEP increased the energy beyond the W pair production threshold. You see this on this very nice plot here. In green, in the middle, you have Petra results. Then the Japanese, that's Tristan in blue. And then you have LEP1 with a peak at Z. And then you have LEP2 on the right-hand side, where you have the measurement without, where you have the measurements with and without production of Ws. And you see the increase after you have crossed the W pair threshold in the light green or light blue or whatever color it is. And if you go to this high energy, then you find very nice free jet events. This is an hadronic, the quark-gluon event, recorded at the highest energy, more or less at the highest energy at LEP, 205 GeV. And you see not only through the higher energy, a much nicer picture, also because our event display has, of course, evolved over the years. And with this energy increase beyond the W pair production threshold, allowed us to confirm the expected self-coupling of the gauge bosons. So in the plot here, you see as a function of energy, the cross-section of the production of two Ws. And it would have gone to infinity without the self-coupling. And with the self-coupling, that's the green line and the green dots, the green measurement points, you see very nicely, it is constrained, it levels off. There is a clear gauge boson self-coupling as you would expect. Again, a very nice and fantastic result from LEP. But now comes an interesting point. LEP is out, since 25 years now. But what should we do? It can never be repeated, I think. So what should we do with the data once the experiment is switched off? Well, very often data are unique, but new scientific questions may require the reanalysis of such data sets. And also new theoretical evolutions are coming, new theories with which you would like, against which you would like to compare these data. So long-term preservation of data from high energy physics experiments is imperative to preserve the ability to address scientific questions at times long after the completion of those experiments. And therefore, the scientific motivation for reusing and reanalyzing data is given by as I already said, in principle, the availability of new theoretical input in terms of increased precision, advanced models, new predictions, new analysis techniques, improved analysis techniques, and the desire to perform cross checks between different experiments. Now, there were at that time no plans for further data reservation and for future use. But then a private initiative, and that's an interesting story, a private initiative for long-term preservation started mid of the 90s at DESY, when a member of the JADE collaboration at DESY organized to copy the JADE data to modern and more efficient data carriers and to preserve the JADE software libraries. You need both things, because without the software library, you cannot re-evaluate the old data. And then, driven by the desire to reanalyze the JADE data in terms of much more advanced QCD calculations and Monte Carlo models, the resurrection of the JADE software was initiated by the professor at the Max Planck Institute in Munich. And the revived software was actively used for new analysis of the JADE data and resulted in 3 further PhD theses, 10 journal publications, and many additional contributions to international conferences and workshops. So this was really, can be seen as a precursor of today's FAIR principle. That means that data should be findable, interoperable, and reusable. And this was the case for the JADE data already mid of the 90s. And that's a result of one of these reanalyses of JADE data. You see again the running of the strong coupling constant, and the reanalysis of JADE and OPAL data, now analyzed with the same algorithm and the most recent theoretical input, proves the running of the coupling constant with even better accuracy and much more striking. So the lesson number 3 is data preservation and reusability is important. But is there something beyond all this? Well, we searched for new physics. And this is an important statement now for the way to look for the top quark and the Higgs boson. In electroweak theory, the corrections in the observables are quadratically dependent on the top mass and logarithmically dependent on the Higgs. So the first thing you would look, is there a deviation of the data from the prediction in such a way that it could be explained by a top mass, which, as I said, enters quadratically? That would be the first thing. And that was our search for the top quark. You see on the horizontal line, the year of the data analysis, and on the vertical axis you see the result for the top mass, which we were looking for. And the blue band or the greenish band shows the indirect measurements or indirect expectations from lab, which started high, went a little bit low, and finally leveled out in roughly 170, 75. In the dark dots are the direct measurements of the top mass in 1990, which was discovered at Tevatron at Fermilab in 1995. And you see the fantastic agreement between the measurements of in the direct evidence and the measurements and the prediction from the indirect measurements. So the precision measurements from the standard model constraints and the direct measurements agree and complement each other well. Again, a fantastic result for the theory, for the experiments, for the international cooperation, Europe and US at that time. Okay, so that's the standard model then at the time, at the end of lab. Still missing the mechanism which gives mass to the particles, to the elementary particles. So one crucial question was left open: how do elementary particles acquire the mass? Now, also, as I said, Lab was searching for it, and this plot shows we couldn't find it. But is there something missing now logarithmically in the standard in the experimental data, which deviates from the standard model? And the Lab 1 data and the standard model require something Higgs-like and within the LHC reach, because the minimum of the highest probability for expectation is between 100 and 200 GeV for the Higgs mass, which is displayed on the bottom. So again, it is obvious that within the reach of the LHC, we should find the Higgs boson, or if we don't find it, we should find the mechanism which is then different to give the mass to elementary particles. So lesson 1, I can repeat: the precision measurements guide the way to the next discovery, sometimes at least. Okay, towards the LHC. The key questions of particle physics at that time, and many of them are still there today, is the origin of mass matter. What happened to antimatter? Which number of space and time dimensions are we living in? What is dark matter? What is dark energy? I mean, the standard model, after all, it describes only roughly 5% of the matter energy density of the universe. 95% are dark matter, dark energy. Now comes the some experimental time, and I have been told I have time as much as I need, so I use a bit more than 1 hour. Large Hadron Collider is more or less the largest scientific instrument ever built. It's in the same tunnel as Lab was before, accelerator of 27 kilometer circumference. Now, instead of electrons and positrons, it collides protons to reproduce the conditions millionths of a second, 10 to the minus 12 seconds after the birth of the universe, with 40 million times a second of collision. And now we really have 4 huge experiments which register what happens in these collisions. And now one word on collaboration. To design and to construct such a project, you need many thousands of technicians, many thousands of engineers and physicists from all over the world, from different cultures, from many different disciplines, to work together, to develop new technologies, develop new engineering concepts, and to work together over decades. And this is something which is many people forget. This is something vital in order to bring us forward. Work together over decades in a sustained way. And the question was at that time, can that work? We need the LHC is the fastest racetrack on the planet. It's 99 point whatever 9% the speed of light. It's packed in 2,808 packets. The protons run around the ring. They are kept on 1,200 superconducting dipole magnets, 15-meter long each, 8 Tesla magnetic field. The operating temperature is about minus 271 degrees, 1.9 degree above absolute zero. It's superfluid helium temperature. The magnets are cooled down to that temperature. Warm magnets could not deliver that, and warm magnets would be out of range to pay for the power cost. Now, during the acceleration, the energy of each beam increases by roughly 300 megajoule within 20 minutes. And during that time, the protons, just to give you an idea, the protons travel a distance further than the round trip to the sun. The energy stored in the 2 beams is 720 megajoules. 700 megajoule melt 1 ton of copper. So you can very well imagine if you are make a slightest mistake, and then you destroy the accelerator. Nothing else will happen, but you destroy the accelerator, and that's the end of the experiment. So we need finely controlled feedback loops to maintain position and stability of the proton packets to extremely high precision. And this is where we used already the predecessor of AI, neural networks. And that we used already from the learning at lab that we brought then further on to LHC. And that's being used today, of course, because a human is too slow. You need AI. Okay, that's again a comparison to here the energy stored in the magnet system. In the magnet system, not in the beam. In the magnet system is 10 gigajoule, which means an Airbus 380 flying 700 kilometers per hour. And that's a view of the tunnel. It's a boring thing. It's 27 kilometers like this, with a view in interaction regions where the detectors are located. So these engineering challenges had to be mastered, and then the accelerator can run. And now you want to do measure. So here in a sketch, the proton beams, they run in two beam pipes, and the protons are then collided at the interaction regions. They are in bunches. Then the proton collide. What interacts are the quarks and the gluons in the proton. And out of the interaction of the quarks and gluons, we produce new particles and we measure the decay of the particles. So the particle collisions are the hottest spot in the galaxy. Its temperature is around 1,000 million times hotter than the heart of the sun. However, what counts is not the energy, it's the energy density, because it's in a minuscule space. So the energy density is huge, and this is how you get to the reproduction of the early universe reactions. A new era in fundamental science started then in 2009, 2010, when these 4 detectors started taking data. You see the 4 detectors as a sketch here. Now look at CMS. C means it's a compact. The C stands for compact muon solenoid. And the compact is, it's really compact, but it's large. You see in the middle of the figure, you see 2 technicians or physicists during the installation. You see parts of the detector, which once the persons have and the scaffolding has been removed, the detector pieces will be slided together. And what I forgot, CMS has roughly 4,000 members from around 40 countries. So again, factor 10 nearly more than the Opal experiment at the time of lab. And that's only look at the sketch. You see here at the bottom of the detector a few figures, and that's to give you the size of the detector, an estimation for that. It has a width of 44 meters, diameter of 22, and it weighs 7,000 tons. So again, one scale bigger and larger and heavier than the experiments at lab. And I like this photo here. During the installation, again, it gives, first of all, I find these detectors are also pieces of art. And again, it shows the mere size of the experiments. The person in the middle gives the scale for the experiment. Again, much more than 3,000 members from, again, roughly 40 countries, not necessarily all the same as in CMS. That photo was taken during the early construction phase. All this empty space is now equipped with instrumentation. And I want to spend one word on large international collaborations, because you might imagine, I mean, how can I work in such large collaborations? But I can tell you, to my experience, it's a fantastic way of learning. It's a place where people learn to work together. as I mentioned at the beginning already, it's a way of collaboration and competition. There is enough competition inside the experiments, but once it's going towards decisions, there is collaboration. You can reach it in different ways. You can make use of diversity. It's a fantastic opportunity to recognize differences, accept these differences, and learn to use them. You profit from them. It influences definitely the way of thinking and of planning. Information sharing. You learn to give because you want to take. If you don't give, you don't get anything. You also realize the role of computing in the internationalization and communication. And that's an experience that you can use as individual and also, to my mind, in other fields. And the world is at present in a state where people should learn much more along these lines. In addition, the management is interesting. It is through common goals. And the only way to manage that is by convincing partners. You must listen to the other, you must argue with the other, and whoever has a better argument is at the end the one who determines the direction. I think large international collaborations are a great training ground for academia and private sector for today's challenging global projects and markets and also the politics. Okay, so we have then finally the detector. The whole volume is filled with 100 million sensors in all experiments. They are of different kinds, developed by over 3,000 physicists and engineers. And then we arrived at an average measurement accuracy of 100 micrometer over the entire volume. So it's a big but fantastically precise instrument, such a detector. Okay, we have constructed the accelerator detector. What next? The protons collide inside this tiny tube to which the arrow points in the heart of the detector once the detector is moved together. Question is, can this work? 1 billion pairs of protons per second, hundreds of billions of particles produced every second, a very harsh environment. Electronics has to be radiation hard, detector has to be radiation hard, etc. And in order to find the Higgs boson, we were looking for physics signals which are roughly 10 or 11 orders of magnitude below the rate of the total signal rate. So all signals together which you produce, only 1 in 10 to the 10 or 10 to the 11 could be a Higgs boson. And to give a scale, the number of human beings is of the order of 10 to the 10. So the job of the LHC detectors is trying to find the one person in all of humanity who meets a special set of criteria. And the critical point, of course, is the important point is the special set of criteria. It works. And the status of the search for the Higgs boson in March 2011, 1.5 years after switch on of the LHC, you have seen the lab precision tests of the standard model. A low mass is expected. Then the direct search from lab and the search at the tevatron here in orange left not much space for the Higgs. There was a tiny window around 183, 184 GeV, and a larger window between 114 from lab and 157 from the tevatron. If the Higgs exists, it should lie somewhere there with its mass. And on the 4th of July, we could announce the discovery that we observe a particle consistent with a long-sought Higgs boson. And this is a very nice event. Yeah?
Train.
Sorry? Okay. The very nice event display from the CMS detector where the two green hadronic calorimeter signals, which could be two electrons, could be the decay of a Higgs into 2 electrons. And that was the discovery in 2012. No, sorry, not electrons, photons, to correct myself. Photons, because there was no track in front of the green calorimeter signal. So this is the mass distribution. If you take the invariant mass of 2 photons, then only with a standard model without a Higgs, you would see what is displayed here. The dark dots are the measurements, and the lines is what you would expect from standard model without a Higgs. But then there was a deviation from that, around 125 GeV, and that's in a large way, and that was enough to have exactly 5 sigma deviation from the background. So this was the very first signal in CMS for the discovery of the Higgs boson. A very similar plot was achieved in Atlas. And very interesting is to look at the signal development during the last 12 months before the announcement. In summer 2011, that's the top. What is displayed there is the probability that if you see a signal of your data in the mass distribution of the 2 photons, the probability that it's compatible with the expectation without a Higgs. So in summer 2011, there was a little bit in which experiment, in the CMS experiment at around 120, and in the Atlas experiment a bit higher at 130 GeV. In spring 2012, half a year later, they reached together more or less at the same place, namely 120 to 125, a 3 sigma indication of deviation from the background. Half a year later, in summer 2012, the 5 sigma threshold was crossed for both experiments, as more or less at the same mass value of 125 GeV. And at the time of publication in December 2012, it was 6 sigma. So it became clearer and clearer. At the same place, the same effect, the same mass value, we had found it. That then gave, in the year afterwards, in 2013, the Nobel Prize to François Englert left and Peter Higgs on the right. 48 years after their theoretical prediction of the Higgs mass, of the Higgs boson. It was an emotional moment. Of course, it made the top page of physics letters. You see on the left, on the top one, you see CMS, the figure I showed, and on the bottom right from Atlas, the probability distribution. Made it into many, many different papers, in all types of papers. But the question is, what sort of boson did we find? And I come to that in a minute. I find this from the, it was the Economist. After science great leap forward, I think this is a fantastic statement. It's not particle physics great leap forward or physics great leap forward. They stated correctly, science's great leap forward. And you have to digest what they wrote on the left-hand side. Let's see at the bottom of the left-hand side. Without the Higgs, no. Higgs makes sense of what would otherwise be incomprehensible. Its significance is massive, literally. Without the Higgs, there would be no mass. Without mass, there would be no stars, no planets, no atoms, and certainly no human beings. There would be no history. So it was a fundamental discovery. And still today, it triggers much interest in society, I can tell you. And my lesson number 4 is good communication to society is mandatory, because we need the money also for research. And the research is not for us. Research is for society, and society also pays for it. So we have to really train ourselves to make a good, convincing, and correct communication and understandable communication to society. Okay, so we have it here. The standard model as it is today, it stands rock solid. All measurements we do are compatible with standard model predictions. It is amazing. And what is even more amazing, this Higgs particle is special. All matter particles are fermions, spin 1/2. All force particles are spin 1. They are bosons. Now the Higgs particle is a spin 0. It's also a boson, but spin 0, no spin. It's a scalar. Higgs is neither matter nor force. In other words, the Higgs is different. And it's the first and only fundamental scalar ever discovered. So the question is, why is there only one? Why should there be only one? Now, could we make some connection to other things like dark energy? Well, this field of which the Higgs particle is the ambassador, the Broad-Anglaire Higgs field, it's a scalar field everywhere equally in the universe. So it must be a scalar too. Can we find through the study of the Higgs some hints on the properties of dark energy, which we don't understand at the moment? And as I said, should the Higgs be the only one? Well, let's see. We don't know yet. Is there a dark matter connection? Here I show again the energy distribution of the universe. Dark energy, say 70%, 25% dark matter, 5% normal matter. Now the Higgs couples to normal matter. But a brother of the Higgs, or the Higgs itself, or the sister of a Higgs, could also couple to the dark matter. They could have also mass from this Broad-Anglaire Higgs mechanism. This is now the point to study. And as I said already, could we learn about something about dark energy, which is also a scalar? So it opens, in principle, a lot of interesting questions, speculations, hopes, whatever. So what is the near future at the Large Hadron Collider? The Large Hadron Collider has gone from discovery to precision Higgs physics. And the interplay, which we had already several times in the talk, the interplay of theory and experiment, it will be even more important in the future. So a continuing program of theoretical calculations is essential to match the precision which we have meanwhile on the Higgs measurements in the experiments. And as it was before from Petra to LAB and now to LHC, precision Higgs physics might be the telescope to high-scale physics, might give some indication there. And this is just a glimpse of the achievement since the Higgs boson discovery. So it's a measurement of the coupling of the Higgs to fundamental particles. The heavier the particle, the stronger is the Higgs coupling to that fundamental particle. And you see on the left, in the left plot CMS, on the right plot Atlas, you see the fantastic agreement between the measurements as the dots and the expectation from the standard model for the Higgs boson couplings. So the precision on the couplings reached is impressive. The accuracy is now already often better than 10%. And so well compatible with the standard model expectation. But also the progress in theory is tremendous. I don't have a time scale here, but it started in, I know the time scale is on the plot itself. In 1978, with easier part of the calculation, namely the lowest order. Then you take the next to leading order, then the next to leading order, etc. And you see how well now, meanwhile, with the more and more refined and more accurate calculations in theory, the experiments and theory agree. An amazing success also for theorists. And this is the input from theory, which is the most striking one. From Nima Al-Kani Hamed, the Higgs is really new physics. We have never seen anything like it. It's a harbinger of profound new principles at work. And here I have the quantum, in quantum vacuum. Sorry, only the vacuum. Put the Higgs under microscope, study it to death. That's the message from theory. And one of the future topics for Higgs physics at the LHC is to measure the Higgs boson pair production, which would give the last missing parameter in its physics part in the standard model, namely the shape of its potential. So the Higgs boson pair production will be a primary physics goal for the high luminosity LHC, which should start in, let's say, 4 years. I think LHC will now go into a shutdown to upgrade it to produce more collisions per second in order to measure these self-coupling. And even further beyond, in 2020, we made an update for the European strategy for particle physics. And if you look on the left in red, highest priority next collider is an E plus E minus Higgs factory after the full exploitation of the LHC and the high luminosity LHC. The next update will come early next year, and it will not change at least the conclusion for the highest priority next collider. That is, I think, already pretty certain. Okay, so what is in front of us? There are many unanswered questions in fundamental physics. And CERN will definitely continue to play a crucial role in the journey of exploration. Thank you.
Yeah, thank you very much for sharing all your insights with us, Rolf. And yeah, today we have a lot of students here in the live lecture, so I'm very happy about this. And now maybe the students can turn on your cameras, so Rolf also has a chance to see you. And we will open up the floor for any questions you may have, whatever it be about CERN, physics. Please turn on your camera so we can see you. And any questions you may have, you can send them via the chat or audio. This is your opportunity.
I put them asleep.
No, I think they were listened carefully. Yeah, Rolf. So let's see. If you have a question, maybe just raise your hand here in Zoom, and we'll see and walk through your questions then. Yeah, Rolf. What about the Illuminati movie? How far is it actually real, and is there any link to CERN? I know the answer, but I'm starting with that icebreaker.
The Illuminati, wait a second, that's not Angels and Demons.
Yeah, that one where
That one.
this movie
Okay.
where you see
With
CERN.
the antimatter.
Yeah, exactly.
Yeah. Well, it's fiction. It's not reality, but it's well made. And yes, we have at CERN, there are also other experiments. The Large Hadron Collider is the most powerful collider, most powerful accelerator, which we built on Earth. But at CERN, we also have the lowest energy decelerator, where we produce antimatter atoms. However, to keep antimatter for a decent time, you have to be sure not to get it into contact with matter, because then it would immediately they would immediately react into energy and be energy. So you cannot store it very well. First of all, you cannot produce much, and secondly, you cannot store it for long. So yes, it's correct. We can produce antimatter, but it's incorrect. We cannot store it, and we cannot use it for whatever negative effects. We can measure it. Yeah. And actually was ist die Uraufführung? The release, the first show of the play was at CERN. And we allowed this because we knew that the CERN director, I was CERN director at that time, was not the guilty guy.
Yeah.
Okay.
The movie, I remember in the movie, they actually could store the antimatter and then it gets used as a bomb. So that's purely
pure fiction.
And in the movie, I think the control center for the accelerator is underground and they actually see the experiment, and it also does not work that way in the real world.
Halfway it works, because at the time of lab, the open control room was below the Earth. It was close to the cavern. Why? Because we didn't have a fast link to the surface yet.
Okay. Yeah.
Okay. And actually, there was less radiation than on the top than on surface. Okay, so.
Yeah, interesting. When I was at CERN, there was also a zombie movie which was recorded by some of the PhD students. Maybe you know that one, but that's also all pure fiction, has nothing to do with reality. So,
but I can tell you it helps you. Because I was once in a taxi in Copenhagen from the university to the airport, and you very often you talk to the taxi drivers, and the taxi driver was asking where I go to. I said to Geneva. He said, "Yeah, what are you doing there?" I said, "I work there as a physicist." So you know CERN? I said, "Yes, I know CERN. I work there." I know what you are doing. I saw angels and demons, and I got so much attracted that I check your web page regularly to know what you are doing. That's it. That's good PR.
Yeah, it is, since CERN is paid for by the taxpayers and they're
Exactly.
interested in it. I don't see any hands raised, but then I'll ask the next question. I remember from our previous discussion that you had a private meeting with the Pope, so Benedict, the German one, and then the successor, because the two popes were interested in CERN and physics. Maybe tell us a little bit what their view on all of this was and how you could help them.
I could not help them, no. Okay. Well, you see, particle physics and the things we are doing at CERN attract a lot of interest in the society, because it's also something difficult to imagine what the smallest, the biggest, etc. So we wanted to make a series of workshops at the interface of knowledge, involving particle physicists, philosophers, and religious leaders. And religious leaders means Christians, from Islam, Jewish, Buddhism, etc. And so I went to the Vatican. I had the possibility to go there because we had some. Well, if you are at CERN, you have a lot of connections, by the way. That helps. So I had some connections. And the first one I met was Benedict. And he was very interested in the science and in the connection to philosophy. So he was, so to speak, the scientist. And then later on, I had another possibility, and he offered the help of the Papal Papal Academy to work with us. So that was all fine. And then I had the occasion to visit Franciscus, and he was more the human. he was more on human, on social science, on the human aspects of the work. So it was very interesting to see the two different characters, but both very interested, and yeah, that was it.
Yeah, fantastic. Thanks for sharing those insights. So I have a lot of students who turned on their cameras. Who of you has a question for Rolf about CERN, about physics, whatever? Please go ahead. Don't feel shy. This is your opportunity. Is any of the students here who visited CERN? Anyone here? Because we have an AI association of students, Rolf, and they organized a couple of tours and visited CERN. So I saw just one person send a yes, but I don't see who that person is. So Erbakan, you were there at CERN, and Elias. So some of the students already visited CERN, and I think that's a really cool initiative by our AI association in the department.
There is also a question in the chat, which just popped up. What do you have to do, or how can you take part in CERN? Well, the question is, well, you can do it either as a as a researcher, like for example, postdoc, if your professor is involved in an experiment or an activity at CERN. I mean, Patrick Glauner, for example, you have a few students at CERN from all the time, I think.
Yes, currently one is there, the other one just finished his
Yeah.
internship. But we also had this recruiting event last month, so we hope that more of the current students are applying for internships.
So you can also, on your own initiative, apply for an internship. Yeah. You can also visit CERN, that you can do all the time. But in order to work at CERN, you have to apply via your prof or on your own initiative. You look on the website of CERN what you can do or how you have to do it. The chances, if you do it alone, is not very high. The chance if your professor brings you there is very high, if he wants to bring you there.
And if there's funding, that's also another.
Yeah, if he has funding. Yeah, sure. Yeah, it's clear. Yeah.
Yeah, so an internship at CERN is definitely rewarding. That's how I came initially to CERN at the end of my undergrad, and then did my thesis, and then got an offer to stay. Rolf, we got another question. So a student refers to a movie called The Peace Particle. Do you know that
Yeah.
movie? And if so, what's
Yeah.
your opinion on it?
If I'm not mistaken, the Peace Particle is a story of how the work developed during the time of the discovery of the Higgs boson. Is it correct? Is the student nodding or not? I can't see any. I only see you.
You should be seeing all the other students too.
Yeah.
Clicked on.
Yeah. Now I found the button.
Yeah.
I found the right button. Yeah.
So I don't know if that student has nodded or not, but maybe just assuming your assumption was correct, just go ahead, Rolf.
I think it's a very nice story, which gives also the human aspects, how the work was during the time of during the period of the discovery of the Higgs boson. If I'm not mistaken, I have not seen it myself. I think I also unfortunately feature in there, but I haven't seen it yet.
Okay.
So it's interviews with different people, and it explains a little bit the story of the Higgs particle.
Good. Since a lot of you turn on your cameras, you can also ask any question live or send it to the chat. And maybe you can tell us a bit more about your current work, maybe about CSAMI, just a few sentences, since we have quite a lot of students or some from the Middle East. So you maybe can say a few words about CSAMI and your role there. That could be helpful.
Well, CERN itself is to some extent also a peace particle, I must say, because it's bringing really very many different cultures together, nations and cultures. And in a similar way, Sesame, that's a synchrotron light for experimental sciences and applications in the Middle East and beyond, is structured, built in its governance along the lines of CERN. But it's a synchrotron radiation facility allowing science and research in many different areas, from physics, chemistry, to biology, medical applications, cultural heritage, environmental aspects, whatever. It is a synchrotron radiation facility in the Middle East. It's situated in Jordan. And the members who are running, which are running the facility, are essentially from the Middle East. It's Pakistan, Turkey, Egypt, Cyprus, Jordan, Iran, Palestine, and Israel. And especially at this time, it is needed more than ever. And it works. People are talking to each other. Not only to, they are talking with each other. That's important. And they are doing research there. Sometimes remotely, but usually in person. So it's a great experience. I am the chair of the council, and we get support from all over the world, from many other synchrotron radiation laboratories, from several countries, etc. So it's to my mind, how to say, it's another peace particle, because you start appreciating the other people.
Yeah, I really enjoyed it there when we traveled there a few months ago and had a conference there at Sesame. And I think it's so helpful for that region to bring together researchers from countries like Iran, Palestine, Israel, and build or foster peace by bringing people together and have them work together. So we got two more questions about physics.
I just want to.
Yeah.
It's difficult to talk about peace because you can say, what is one facility doing for the peace? I prefer more to say that CERN or Sesame, they build bridges between cultures and nations. I think that's a much better expression to my mind.
Perfect. Thank you.
Also, yeah.
Yeah, so one student here, Dominic, asked that you were talking about antimatter for a bit, and maybe you can share what some ways are to keep the antimatter particles alive.
You use the dipole moment of the atom, and you have a clever arrangement of electric fields and magnetic fields in order to keep it in a highest possible vacuum. But since the vacuum is never indefinitely small or indefinitely good, you always will have reactions between the particle and the remainder of the gas. So it's only for a short time, but you can hold it for enough time in order to do measurements. For example, nobody said that antiprotons or antimatter falls like matter. It could well be that it falls the other way around. That means that it goes against gravity, but they could prove it falls as matter. So for the moment, they have not found real differences between matter and antimatter, and they continue measuring. I think CERN is the only place where this is being done.
Yeah, thank you. The next question is wondering, what do you think which discovery in the near future would most fundamentally reshape physics, or is that too difficult to predict, and what do you hope for?
I would say it's too difficult to predict, but what would I hope for? my hope still now for particle physics, my hope is to understand the origin of dark matter. What is dark matter? Because that is something which could be reachable because we can measure things where dark matter has clear influence. Dark energy is even more difficult. But I think at some stage we must find more of the asymmetry reasons between matter and antimatter. I think it's a question of accuracy of the measurements. So there's one experiment at the LHC, which I did not mention because the talk was anyhow long. That is LHCb, which is particularly measuring the difference between matter and antimatter, with high accuracy. But well, that would be for me something which would change things.
Okay, cool. Then Nikhil is wondering how modern machine learning is used in CERN, especially for particle identification and optimization.
Well, first of all, we used it already at the lab times, but then
I cannot hear Rolf anymore. Can you hear him?
Nope. We also lost connection with him.
Yeah, we lost the connection. Rolf, can you still hear us? We'll just wait a moment. So I had interrupted the recording and I called Rolf on his phone. He specifically went to CERN so the internet connection works because sometimes he has internet problems at his private home, but CERN had a power outage. So he's unable to go back online. So his original goal of going home or of going to CERN to have the safe internet connection unfortunately did not work. And he's very sorry, but we could answer most of your questions already. And I hope you enjoyed Rolf's guest lecture, and I want to thank him here again. And he will anyway see the recording. And we will stop this recording now, and we will switch to the lecture with a new recording.